Hi, everyone. Welcome to the second day of the Diversity in Energy Transition Symposium, a collaboration between our three universities here at TU Delft, TU Delft, IIT Bombay, and NTU Singapore. We've had such a great day for day one, so many amazing speakers, really great questions, and we're looking forward to get pumped for day two. And tomorrow we will be doing a big researcher collaboration discussion on a Discord channel. If you'd like to join us, please look at our emails and join then. So it is my honor to introduce today our first speaker, Professor Arno Smets. He is a doctor from TU Delft University. He has worked in Japan as well. And his research focuses mostly on the processing of thin silicone films, innovative materials, and new concepts for photovoltaic applications. But not just that, he does many more things, and I will let him continue from here. Thank you, and please welcome Dr. Arno Smets.
Thank you, Alice, and thank you also the co-organizers for inviting me today. To give an hopefully inspiring presentation on the role of solar energy in terms of tackling the challenges we're facing with respect to climate change, but also access of electricity to many people around the world. So I will also discuss the role of solar energy in energy transition scenarios and some technologies status, but also I will discuss some next generation technologies. Okay, Alice already mentioned, so my research is focused on working fundamental materials to applications on all kinds of innovative technologies in converting solar energy into electricity or into even fuels. And also at the university, me and the colleagues have developed education with respect to solar energy and also online education. So we have different micromasters or massive open online courses on the internet where we reach out to students and professionals around the world. So talking about solar energy, the source is this very hot object which is in the center of our planetary system. And this is the energy source. It's the energy source of many of the processes which occur at the surface and in the atmosphere of planet Earth. And strange enough, it is also the source if we look at one of the problems which we are facing. So if we look at the thermal budget of planet Earth, of course, the atmosphere, there is a lot of energy coming in. It's the solar radiance of the sun. And as the Earth is not at absolute 0 Kelvin, it also emits with a kind of, in the far infrared, it emits electromagnetic radiation. And so if the amount of energy coming in or power coming in is equal to the amount of energy power going out, basically the temperature stays constant. Now, is this the case? The CIRRUS project of NASA, they tried to measure this, and it was an enormous challenge, of course, to do that. But the first estimates are that in the last 20 years, around 0.6 watts per square meters of power is left behind. So it's an imbalance that stays on planet Earth. If you make a simple back on the envelope calculation, this is already sufficient. If all this energy would be converted into thermal energy within the atmosphere, you would increase the temperature of the atmosphere with 1.8 degrees Celsius per year. This is of course not happening because we have enormous heat sinks on the planet, and that is the ocean, the waters which we have. And this is all happening because we are creating this blanket of greenhouse gases around in the atmosphere, which partly blocks a small fraction of this infrared radiation emitted by planet Earth. This is cause of the imbalance. So if we would look at how does that compare to the total energy which we currently consuming, primary energy consumption is 65 kilowatt hours per day per person, and that equals around 0.03 watt, 4 watt of consumption if I would average over the total area of planet Earth. So you see that our current energy consumption is even less, factor 20 less than this imbalance. So basically, the emissions which we have put in our atmosphere already have a bigger impact on the energy imbalance than the energy which we're converting from sources into finally heat. So it is quite interesting. So what you can do is, of course, make the planet more reflective. That is one solution. But another solution is also stop using those energy sources which emit greenhouse gases like CO2. And so which energy source can we use? Which one is available? Of course, the solar irradiance coming in would be a very logical choice. And basically nature is already doing that for millions, billions of years using the photosynthetic process in which solar irradiation is being converted using carbon dioxide or water in carbohydrates. And so this is the source of life. Those carbohydrates are also the energy source for the engine being our stomach. And here you see how the photosynthetic process is being active over the seasons over the planet Earth. So what you see over here is the conversion of solar light into a chemical fuel, being those carbohydrates. So nature is doing that, and nature has also a certain efficiency. And let's look that. This is a kind of back on the envelope calculation. If you look at how much biomass is being created and how much chemical energy is confined in the biomass, and if I smear this generation out again over the total surface of planet Earth, I come around 0.5 watts per square meters. That is the solar to fuel cell being the planet Earth. That's the efficiency. And so on the vertical axis, I have the total chemical power being generated. Then I have on the horizontal axis, that's basically a timeline. So we're looking here at the last 2,000 years. And the blue line you have here, the vertical line, is the world population. So you see how the world population is quickly growing, certainly after the industrial revolution. So all those people, I've already mentioned, we have to feed ourselves. So we need some chemical energy from this chemical power flux of the photosynthetic flux. And if you do some back on the envelope calculations here, it means that around 7.5%, with all the losses, of course, in this value chain, we eating plants or we eating meat and stuff like that. It means that 7.5% of this chemical power is already only needed to feed humans. And if you look at our typical energy consumption, which is all the other needs, is 20 times of what our body needs, then we see that we are already approaching the limit of what planet Earth is converting itself. So it means that we basically have to cut down every tree, we have to fish every algae growing to provide our energy needs using biomass. So this demonstrates the enormous challenge we're facing. So growing world population also means we have less land area per person available. So in Europe, we express this usually in the area in terms of soccer fields. So this is the land area available in 2050 per person on planet Earth. And in the Netherlands, we are a very poor population because we only have a quarter of field. So it depends on which region you're living in the world, but on these areas, you have to produce your food, you have to live there, you have to generate your energy. And these are the challenges. So certainly in heavily populated areas, we are facing challenges. So what is, if you look at the generation side, what is the challenge? Let's put it in this map of the world. Currently, our energy needs average over the planet Earth is 65 kilowatt hours per person per day. This primary energy need. And let's assume that we would generate this with solar electricity. So with current technology, and here I assume, for instance, a 17% conversion efficiency for solar modules. And here I assume that we store this again, this energy, and 50% is being lost in this cycle. So with our current energy need, how large would this area be, which we should cover? Then you arrive at an area like this, 1200 by 1200 square kilometers. This is a similar area which we already have covered with asphaltus, concrete, roads, and stuff like that. But now we have to do that with a high-value semiconductor product. Is that possible? What are the challenges here? Supply chains and materials. So this is the challenges which we are facing. Of course, another option is to do that with wind electricity. And let's say if we have offshore installations and we would do all electricity generation only by wind, you would arrive at a service like this offshore. So you already see that we need a mix of many solutions to even tackle this problem. And here I'm only talking about generation, because the energy infrastructure is generation, distribution, storage, and consumption, which in all those value chains, you can improve the system efficiency, of course. So what is the challenge already? I mentioned climate change, and here you see the Paris Agreement. It's now more than 5 years ago, in which almost 200 countries around the world committed themselves to introduce policies to reduce the temperature increase of planet Earth in reference to pre-industrial times with not more than 2 degrees Celsius. And it would be very nice if we could limit it to 1.5 degrees Celsius. And it means that we have a limited budget of CO2 available, and you are most probably familiar with all these type of papers where they show like, how long can we continue with emitting the CO2 as we're doing now related to our energy consumption? So it's rather challenging to keep it under 1.5 degrees Celsius, and it means that we already have to significantly reduce our CO2 emissions by 2030 and be CO2 emission neutral around 2050. Enormous challenge. What are we doing? So currently, this is up to 2019. We did not demonstrate yet that we are realizing a reduction in the emissions yet, although a lot of countries have ambition. So this challenge, let's think big, and can we? So here we see, for instance, an energy transition model of the International Energy Agency, and here they look at business as usual, the current policies promised by governments around the world, and the sustainable development scenarios, and the contributions of all the different technologies along this value chain. So talking about renewable energy generation, distribution, but also very efficient consumption, moving to electrical vehicles, and also looking at carbon capture technologies. Another inspiring energy transition model is here from the Energy Watch group. For instance, one of the co-authors is Christian Bayer from the LUT University in Finland. And this is quite an inspiring energy transition model, because it has a very high resolution. They include every region around the world, and also the time resolution is very significant. It's a model in which the don't need carbon capture technologies, and they use current existing technologies. And here you see like that in their model, in the energy transition model, that globally electricity can become the dominant energy carrier. So fossil fuels is phased out in this model. And here you see how, looking at generation side, you see that in reference to the current situation, let's see whether I can use a pointer here. The current situation dominated by fossil fuels, you could move to a situation where you have dominantly solar energy, a large fraction of wind energy, and some other technologies contributing to the energy generation mix. And interesting is that in this model, they demonstrate that you can do that at the same cost price of levelized cost of energy, how it is often expressed, as we have currently. So it doesn't mean that the energy becomes more expensive. And here you see how over the different technologies the investments will be, and you see that solar will be a large part of this portfolio. The interesting thing is, if you look at all the energy transition models being presented around the world, and often it is the International Energy Agency, or it's a certain company or industry like the gas or oil company, or it are scientists or our governments or regional governmental organization, they all find different results. So here, this is a paper which I co-authored with some people. We last year organized at the IEEE PVSC conference in America, where I was the program chair last year. We had a special session on towards 100% renewable energy future. And we had many speakers with experts in decarbonization of many sectors like mobility, industry. And with those people, we have written this white paper just published in Joule. Solar photovoltaics is ready to power a sustainable future. And here we have this graph over here, which shows all the dots here are energy transition model scenarios published. And what you see here, vertical axis is the total wind penetration, and the horizontal axis solar penetration in the energy mix as they predicted. And you see, you can almost get everything in these models. So it's also very important to realize is that what is the method used in these models? What is the time resolution? For instance, here the primes models, which are, for instance, used by the European Union, they only have a time resolution of 1 year. So you miss a lot of the dynamics of an energy infrastructure in that. And here you have a lot of models, but there's also the assumption on role of biomass, limits of land area. And the biggest problem in these models is if you look at, for instance, the cost price. So the majority of the models, they use cost prices of, for instance, solar energy of 15 years ago. And of course, you get different results in your final energy system. So the model I just showed, the Energy Watch group, that's related more to this point over here, this reference over here. So the amount of solar electricity in the future energy system is, in my view, underestimated by most of those energy transition models. And it's based on an assumption that the cost price assumptions are basically already outdated, which are being used in these studies. Another interesting thing is, of course, we're talking about solar energy, and we have, of course, generation, distribution, storage, and consumption. In the Netherlands, for instance, we are on a latitude of 52 degrees. We have high fluctuations between summer and winter in terms of solar irradiance. And here in this plot, you see like the difference between, on average, the solar irradiance in the summer month in reference to the winter month. So the month in which you have the lowest irradiance. So if you see around the equator, of course, this fluctuation is relatively small. And interesting, 50% of the world population is living in these areas. If you look at the Netherlands, here we have a large seasonal fluctuation. So we have even affected 2 more solar energy now in June, which is a very sunny month in reference to December, January, which are very depressive, dark months in the Netherlands. So it means that here you need to tackle the seasonal fluctuation, why in other areas around the world you don't need that. So it also means that the storage systems you will have to use might be different. So here battery technology could already give a nice solution. Whereas up here, you need complementary wind energy, but you also have to think to solar to fuel type of approaches to tackle seasonal fluctuations. And it's also important in terms of, if you look at energy consumption, it's related also with wealth, the living standard. So the more energy you use, the higher the living standard is. But also if you look at energy versus society, which living standard, which economic opportunity can you offer to your citizens? Here I have the energy use per capita plotted versus the type of society you have. So this is typical modern society. This is an emerging society where you have very energy intensive industries, and then you go back to advanced agriculture society and primitive society. So that differs the amount of energy being used. And there's also still a social difference in access to energy. Here, for instance, average in the world is 65 kilowatt hours of energy per person per day. In the Netherlands, for instance, here is 125 kilowatt hours per day. US is even double than that. Here's an example, Indonesia, 25 kilowatt hours per person per day. But if you, on average, continent of Africa, only 12.5 kilowatt hours per person per day. And some of the countries are even at the level of 4 kilowatt hours per person per day. So here, giving access to energy, electricity, even a technology like solar energy, where you can have autonomous systems with PV and a battery, is a very cheap route to give access to energy, but also to give opportunity, improving living standards, but also giving opportunity in business model and improving local and regional economies. So energy access is also a very important topic in that sense. And certainly these regions, they are in the range in which you, with a relatively simple energy system, you can tackle these problems. Okay, let's think big again. What are the challenges and can we think big? This is an example. When I started my PhD on processing materials for solar energy, that was in 1998, and their International Energy Agency, they also had an outlook, and they thought like around this time we would have around 2.5 gigawatt peak of electricity installed. So 20 years ago, our energy agency predicted that we would be over here around this time. So what did we achieve? We achieved this. So how can it be that we as energy specialists can underestimate the development of a technology 20 years ahead with a factor like 250, 300? So we are really bad in predicting the future in that sense. So if you look now what we have achieved, so we have now around 600, 700 gigawatt peak installed in the world, and they are distributed over the regions like China, Europe is Germany, it's around 23%, Japan, North America. Here you see where currently, like the photovoltaic installations, how that's distributed. If you look at the models as predicted, I already mentioned like Energy CC did a very bad job. And if you look at all the models, which I already showed, there is still even a big range of values where we will end up. So usually models underestimated. One of the reasons why they underestimated, as I already mentioned, is that the cost price due to advancement in the technology, but also due to advances in upscaling of the processing technology makes, for instance, the module cheaper and cheaper. Here you see, for instance, a graph of PV system prices as they're being adopted in many of the models I showed. So currently the average system price is the star, which you see up here. And the black dots over here are many of the models, also like the integrated assessment models of the IPCC. They use already outdated data for 20 years ahead cost prices which are more expensive than what has been realized now. And of course, if you use this outdated data, you will get in lower penetration depths than if you use the correct data and also the predicted cost prices of the future. So believe in advances. So what is the challenge and how can we introduce energy? So here you see the history of hydroelectricity, like in the late 19th century, the Francis turbines were invented and implemented in small hydroelectricity dams. And of course, this technology was scaled up. Here you see in the technology of nuclear, the nuclear technology. So in the 50s, it was realized that you can use this technology also to generate energy. And you see there that these technologies show an exponential growth, a linear growth, and a saturation phase. And that's usually related to how fast it saturates to the lifetime of the system. So hydroelectricity dams, they have a lifetime of 100 years, while a nuclear plant currently has a lifetime of 22 years. And that demonstrates how fast you can penetrate it. So how fast you can penetrate that in your energy mix. Here you see the effective power. So there's already corrected for the capacity factor, how fast wind electricity and PV electricity are coming up. So I already showed a different energy transition model. So if I take, for example, the energy transition model of the Energy Watch group, what do we have to achieve? How far do we have to come? So this is the objective for PV and wind. So it still shows that we basically have to stay in the exponential growth phase of wind and PV for 10, 15 years more. So currently, so I don't know whether you can see that here, these are the dots, that are the current predictions. So it looks like that wind electricity and also solar electricity is slightly leveling off. So we need still more investment in that for upscaling this to meet the targets I show here. So if I look at the most pessimistic scenarios, is that we would end up here and that would be way too low. So still we need incentives in the financial sectors, but also with policies to ensure that we are going in this green direction and not in this red direction. And what does that mean? It means that we need a 3 to 6 terawatt peak annual market. So a market which is like 20 to 40 times larger annual market than we have now for photovoltaics. And we have to have that for the next 13 years to stay at this sustainable growth. Of course, it's advances in technologies. I will come back to that. So here you see the current increase in conversion efficiencies over the years of the PV modules. So there's advances in technologies, and these are some ideas where we want to be. But also interesting is looking at the lifetime. Typical lifetimes of PV systems are 15, 20 years. And so here I have plotted from the years from installation. So what you see is here you see the exponential growth of installation, but this is the time where these panels need to be recycled. So that is a challenge which we start to face also in the coming 10, 15 years. We have to recycle all those panels again. So moving to a circular economy. So we also need to create technologies that can facilitate that. Other thing is the supply chains of materials. If you look, for instance, at the lithium-ion technology in batteries, there we're facing challenges in the supply chains of cobalt, of the lithium. For other technologies, nickel. So for the most rare element used in PV is silver. So here you see already the progress in the amount of silver is being used or expressed in the mass per power. So basically you want to use as much as earth abundant materials and also replace silver and PV. So also progress is being made there. So these are all challenges if you have to think about PV technology. quickly to show what does it mean. So here, these are learning curves, and that's also one of the reasons why all those energy transition models, many of them underestimate the role of PV, because we as humans, we cannot think in double logarithmic plots. So this is the learning curve of the cost price of PV modules, and you see that every time we double or the total cumulative installed PV power, basically the cost price is being halved. So this is something which is the power behind the success of the integration of photovoltaics at the moment. Of course, we're talking modules. PV systems are more than only modules. It's all the balance of systems. And what you see is that those components don't drop that fast in price. So at a certain point, you will be limited by the materials used for the racking, the wiring, the inverters and stuff like that. So these are typical cost prices in the Netherlands achieved, but I also have here more typical plots where the green is traditional electricity generation technologies based on fossil fuels, and you see that onshore wind and solar electricity are getting in the range or even getting cheaper than these technologies. So in terms of electricity generation, PV is making enormous progress. Then we also have other metrics which are important. So how much energy do I put into a photovoltaic system, and how long does it take that the energy is being returned? If it takes much longer than the lifetime of the system, then it's of course not interesting. So here, this is a study of Fraunhofer, an overview, and here you see that the energy payback time of PV systems, certainly if you look around the equator, it's very short. Within a year, a system, the energy is paid back. And of course, if you go to the more darker regions on planet Earth, so like in the Netherlands, so there it takes 1.2, 1.5 years before you have an energy payback time, if the energy is paid back. So if you have typical lifetimes of 20, 25 years, you can see that a system delivers at least 20 times the energy as in its lifetime as is being used to create it. So in the Netherlands, for instance, we have challenges as well, because we have not much land area. So the government is net metering. So there is a stimulation policy that for residential PV. So if you feed back solar electricity into grid as a consumer, you get the same price as being paid for that. So this is a policy which will be, the coming 10 years, will be reduced to zero because systems are getting so cheap. But if you look at large-scale utility, their government also has certain subsidies to accelerate these kind of things. And mainly the SDE plus subsidy, so the large-scale utility at the moment, because the Netherlands is still doing a poor job if you compare it to the neighbors in the European Union. So there you see currently an acceleration. Black is wind energy power installed. Red is photovoltaics. There we are closing this gap very quickly. And at the moment, it's one of the biggest PV markets in the world. Here you see, for instance, where to place the PV in a country where you're limited by area. So here we are looking just at industrial roof, so industrial buildings, company buildings. If we would cover these buildings with PV, then you would already achieve the target set for 2030. So also in the urban environment, you have many services available. Then, if you look at here in the Netherlands, these are the grid companies which are responsible of the electricity grids. And in the Netherlands, you see that you have various companies facilitate the electricity infrastructure. But now the problem is, and it also shows that you need integral approaches. Of course, you have incentives to increase the solar electricity generation with a large-scale utility, but it also means that the whole infrastructure, so your electricity grid, also needs to be scaled up. So if you have an incentive and push somewhere, it also means that you need to have policies that the infrastructure of the electricity grid is being scaled up at the same pace. And there you still see some challenges, of course. And here you see, for instance, some regions where the electricity grid is facing some congestion problems. So this also shows that you need an integral approach along the whole value chain of introducing those new technologies. Next to that, of course, public opinion is also very important. If you are limited by land area, it's also very important to have society on your side. Not that we don't want to have a wind park next to our door or a large-scale utility solar park next to the door. So you also have, and what is the health issues related? How does it impact environment? Which materials are being used? So it's very important also in this energy transition to inform and to have ownership of these energy systems with society. So in the Netherlands, we have a discussion on many topics, and one of the topics, of course, land area is limited. So where do we have to install? So first, we would like to use the surfaces, but in the Netherlands, we also have a lot of area on the North Sea. So as we are limited by area, it is also very interesting to look at floating system. Can we use a small part of the sea area to install PV? Okay, if you talk about photovoltaics, we also talk about technologies, and here you see all different types of technology. Usually they are categorized by the materials being used, semiconductor material used for the technologies, and you see here how the conversion efficiency of these technologies have progressed during the last 50 years. So you see there is a lot of progress going on. And although this graph is being used in many presentations, solar energy, which I showed, it's also comparing apples and oranges, because some of the technologies are very mature. Some of those technologies are just being demonstrated in the lab and are not reliable enough as material to put in a product with a lifetime of 25 years. So yeah, the most dominant technology, it's 95% of the world is based on crystalline silicon. Here you see an example of a module, and here you see the typical conversion efficiencies. And I always prefer to plot it as function of the area of the device, because it also shows the maturity of scaling up the technology. You also have different other technologies. So the most efficient PV technology is based on 3,5 semiconductor materials. It's a material which is quite expensive to process. So it's mainly being used for space applications or for concentrations. So for applications where cost price is not really an issue, but that is giving the record conversion efficiencies. And then we have other technologies which we refer to as the thin film technologies, in which, for instance, calcitonin is based on cadmium telluride, or CIGS, copper, indium, gallium selenide sulfide, and also thin film silicon. These are technologies which are being used. And then we have some new kits on the blocks based on perovskite solar cells, organic cells, but these are still in a fundamental research phase, and they are not commercially available, but maybe they are in the future. So if you look at the technologies, and I already mentioned that silicon is the dominant technology, there are you need some materials, and solar cells are based on silicon wafers, which are thin slices of silicon. And here you see two types of, one is the multicrystalline, that are wafers like this. That's usually materials which a little bit more defects in impurity, but it's cheaper to make than, for instance, the monocrystalline, that's this wafer here, which is basically also used for the chip industry. So here, making solar cells of this will give solar cells with a lower conversion efficiency. This will lead to solar cells with a higher conversion efficiency, but slightly more expensive. So that has been a competition going on. So currently the trend is that the monocrystalline silicon is winning it from the multi-silicon because it can be produced relatively cheap and still have a high conversion efficiency. So most technology which you see are based on the crystalline silicon. So what are the technologies which are being used? So this is the working horse basically of the PV for a very long time. You had a wafer, back contact was an aluminium paste, aluminium in diffusion into the wafer at the front side, an N-type emitter layer. So this has been the standard cell for a long time. And now industry is moving to this where basically this back contact is being replaced by point contacts. Why is that? Because at a metal semiconductor interface, you have recombination losses of the charge carriers, light excited charge carriers. And with this, you tackle that fundamental problem, which results in higher conversion efficiencies. So these are the technologies. And other technology invention is at the moment that as this interface between metal and the semiconductor material is one of the limiting interfaces, you can use, for instance, new tricks. Here it's more a quantum mechanical trick where the majority charge carrier, which needs to be collected here, can be collected. It's being tunneling through a barrier, and the minority charge carrier, which is responsible for the rate of recombination losses, you can screen that away. And so this is called the tunnel oxide passivation TOPCon. That is also technology which is being upscaled at the moment, and it's quite interesting because this you can do relatively cheap, also achieving high conversion efficiency. This is another technology, heterojunction solar cells, in which we use an amorphous material to make junctions to on the top of the wafers, in which we can separate the charge carriers generated here in the wafer due to light absorption. This is heterojunction solar cells, and this technology also, if we put all the contacts at the back of the surface, so an interdigitated back solar cell, has resulted in the highest conversion efficiency, 26.7, 26.6% by Japanese company Kaneka. And here, for instance, Delft University, colleagues of mine doing also a lot of research to study all these different configurations to go to very simple architectures with earth-abundant materials, which can be processed in cheap ways. And here you have the different models. So going from a cell to module. So here you see the monocrystalline wafers. You're going to wafers, and you have to put them in models. Models are usually a back sheet, a front glass with an encapsulation frame that makes the whole photovoltaic module. You also have innovations in where you put also a transparent back sheet and a glass panel, so that you get bifacial, so that also the scattering of light from the back is generating solar electricity. And these are all kind of innovations going on. So you also have the thin film technologies, and here I show of course we're talking about the lab scale conversion efficiency, what is on the market and what are record modules. So you see there's still a challenge. What we can do in the lab, we have to upscale that in the same way in production. So still a lot of progress is possible in advancing these technologies to go to higher conversion efficiency. And here you see monocrystalline and some thin film technologies. And let's see, how much time do I have left? Okay, not much time. So here, this is, for instance, where I'm working on at Delft University together with a company HyET Solar, is looking at the next generation solar panels, lightweight, earth-abundant material to make these modules, which we can cover surfaces not available yet to be covered by solar panel, but also going to very cheap floating systems, where the balance of systems of the floating structure can be very cheap because it's a very lightweight technology. And here you see, and also you can go to very cheap large-scale utility systems and also very niche building integrated PV systems. And this is an example, thin film silicon technology, which we are developing here in the Netherlands with very innovative processes where we're not using glass anymore, but a temporary aluminum foil to create this solar cell. That's innovation where researchers and also students at our university are working on in realizing this very innovative processing technology. And with that, I would like to conclude this presentation. And before I conclude this presentation, I want to thank, because I would show you the main conclusion of my presentation, and let's see whether my computer can handle all these slides. So the main conclusion is the title. As you see, what I showed, the solar energy revolution is only getting started. Thank you. Here you see all my colleagues, which are working on a variety of topics from fundamental materials to systems. And I also would like to show here our online portfolio of education, which for a bachelor, master, we cover a lot of the topics of solar energy. Some of them you can find on the edX platform, and also our solar energy book, which introduce you to all these concepts as well. With that, I would like to thank you for your attention, and the word back to Alice, because are there any questions from the audience?
Yes, thank you so much for a wonderful presentation. We have a few questions. We can start off with the first person has said, "Sir, solar cells are very hard to recycle and cannot be reused after it gets old and degraded due to the material used. Used in the making is very toxic to the environment. So what are your thoughts on this, and what can be done regarding the expectation of solar energy?"
That materials are toxic. So what we are using in solar, so certainly crystalline silicon technology, I don't think that the materials are toxic. And this even, the materials are based on the first 30 elements of the periodic system. That's basically the materials you need, certainly for technology which you have to upscale. Having said that, of course, there are technologies under research where you might have components which could be toxic. For instance, cadmium telluride is the discussion on the cadmium and tellurium in there. In the perovskites technology, which is now being researched by institutes, you have lead in the material. But I would say that we should use materials which are mainly from the abundant, and also the choice of technologies which we want to implement should be based on earth abundant material, non-toxic materials. Talking about recycling, and that's again also which technology are we talking about? It should be, is it easy to recycle the materials? If I look at crystalline silicon, so using the whole supply chain, which I show from the quartz side up to, for instance, the silicon, starting from already an old solar panel, you need less energy compared to reuse this material again for new solar cells than the energy required from ore to the silicon supply chains. Having said that, it still means that a lot of innovation and research has to be done to scale this up. And that is one of the challenges indeed for the PV industry and for solar energy in general, to tackle that problem in the coming 10 years. Because in 15 years, as I demonstrated, the first big generation of solar panels will be at its end of its lifetime. And we have to use those source materials again for the new panels.
Thank you for that answer. It's very, very informative. The next question is, hi, Professor, do you think the focus from targeting individual consumers to install solar should shift to targeting electricity generating companies through non-renewable sources in the day to install solar all over the city? By doing this, we can save on the cost of installing batteries and making solar more economical.
So yeah, the approach is also depends fully on the region. Like the Netherlands, a relatively urbanized area, and there you have just a discussion on should we waste our agricultural land for large-scale utility PV, or should we first start using our facades and roofs in the urban environment itself? Also, one important factor is, I guess, is ownership itself. Like if you have a local initiative, so it means that citizens can become the owner of their own energy generation again with either you're having your own PV system on the roof, or as a small corporation having your large-scale utility facility nearby. I think that also brings power back to the people, but certainly also solar power to the people. So ownership in that sense is also important. Then only that some big multinational companies are dictating this energy transition. So in that sense, this technology also offers opportunity to have a more democratic energy system. But also depends fully on the region. So in the Netherlands, that is one of the regions in the world where we might be limited by area, but in most regions in the world, we're not limited by area. And it also depends on the local energy market. Some energy markets are more subsidized than other ones. So which incentives do you need to get a solar energy market started? So it's not one-to-one, but one of the advantages of solar electricity is that it can give solar power to the people, in not only in the power itself, but also in the ownership of the systems.
Thank you. And I think we have time for one more question. Hello, Professor. What are the cons of artificial photosynthesis? And is Singapore adopting artificial photosynthesis process on solar panels currently?
We're talking about all the solar to fuel, solar power to X kind of approaches. I think certainly for regions with a higher latitude, this is very essential. So for instance, in the Netherlands, there is a lot of interest currently in green hydrogen. So we have renewable electricity and we start to convert that into a fuel. It's very important. It's also important in the sense that we still have a refinery. So fossil fuels is also being used for industry, refinery, for plastic product and stuff like that. We also have to think about CO2 reduction methods in which we use energy where we then produce the chemical resources for industry also in a renewable manner. So if I look at the industry, it's very important. Also in production processes, making steel, currently a lot of gas is being used. You can replace that, for instance, with hydrogen, certainly in downstream after the blast furnace step. Only electricity won't do the job. So I really think that also converting solar electricity, wind electricity, hydroelectricity into fuels is an important step. And also to tackle seasonal fluctuation, as I mentioned, for the high latitude countries like Canada, like Scandinavia, Germany, and which we have all around the world. So they're tackling seasonal fluctuations, solar to fuel is very important.
Okay, thank you so much. That's the end of our time, but I'd really appreciate you coming today and talking about this. We had some great questions from the audience, and if you don't mind, I can send them along to you and maybe you can answer them. And we'll send it out with the emails after day 3. But thank you again for participating and presenting such a wonderful lecture.
Yeah.
Thank you.